some of this now. What else have we got left? Suppose we want to write a toString, just for the pure fun of it. Oh, one other thing I was going to mention before we write a toString. Look at this piece of code here. If you're seeing it for the first time, what's the most interesting line in the code?
I'd say the for int.
What was the most interesting thing that we saw in the diagram to begin with? When we started and we said we're going to remove this one. We said the most interesting thing when we remove this one is, oh, okay, if that one's going to remove, then that one's got to move one position backwards.
Yeah.
Okay? So if that's the thing you keyed in on here, the thing I want you to learn when you're reading code is to find the same line in there for the problem and go, that's the interesting portion of the problem. Oh, look, something's moving from where it is now one position backwards. Oh, look, they're doing that a whole bunch of times going in a forward direction, which is exactly what we expected to see here. Okay? So, good thing about reading code when you get experienced at it, you don't read code from this way in, particularly when you see loops. You start in the middle of the thing because that's where all of the excitement and action is that tells you what's going on. Everything else is just set up to get that thing into play. Okay? And so it's actually almost best to read it from the inside going out. And I'll make the suggestion that when you're writing it, it's also probably easier to write it from the inside out and say, well, if I want to make one of them move, how do I make one of them move? Oh, now I have to make all of them move and work your way outside, which is contrary to the way that they ever teach you. They always say write it from the outside in, and that's usually what gets people all squirmy. Okay? So if it's not working for you going in that direction, start from the inside out and see if you can work it from that direction. Okay? And if you think of it in terms of what I'm trying to do when I'm looking at code is reduce the amount of code that I have to worry about, right? I'm trying to ignore code rather than read code. Then when I see that, I have a good idea of what's going on with the thing. So that's exactly the same reason why I say if you write ifs in the rejection style, you end up with a bunch of code you don't have to read that you can ignore because there's just too much code to read, too much detail. I want to find the interesting stuff first. Okay? So we're still playing the same game. You'll see me go right for the loops. Okay? If you look at GUI code, all GUI code is set up except for the stuff that's inside the action listeners, or whatever the listeners happen to be. That's where all the good stuff is, so you can go find those and ignore most of the other stuff in the code because it's sort of profoundly uninteresting. Okay? So there's some good rules of thumb for reading code. Okay, so let's write a toString just for the pure fun of it. And the easiest way is to say string result is nothing and send it back eventually. What should a toString do for a list?
Get each item of the list and print up all the information. Yeah.
So the idea is that if I say system out print line of just the list variable, you'd expect it to dump out the entire contents of the list. Okay? Let's work this one backwards. How would you get one thing from the list? So I would call the toString of that thing and I would append it to result. And then if that did just one of them, I'd want to do it for all of them. So I'll put that thing into a loop. What kind of loop do you want to write?
For each.
Pfeiffer trickery. If I write a for each,
Count as loop. 'Cause it will do the
what's it
blank
going to
ones.
do with these items?
Print out blanks.
It's going to print out empty stuff for those, and there could be a whole lot of empty things. Okay? So I really only want to print out the full things. Okay? So one of the sad things about for eaches is that you can't do this sort of thing easily with a for each. So you're stuck with a counted loop, because for each by its nature wants to do all of them, not just some of them.
That could be handy though, to see how many empty spaces you have.
Well, nah, not really. Not really, because there can be a lot of them. And so the easy thing about, the easy sort of takeaway about for each is that if you're writing code that's using positional notation, chances are pretty good you're going to get stuck with using positional notation all the way through, and at the very least that's consistent. Okay, so automatically, since we've been using positional notation for anything else, this thing becomes positional notation also. So int I equals,
You can just say ignore it if it's null.
no, we don't want to, the nulls are all at the end, so I is less than, how many items are on the list?
Next free to fill.
Next free to fill is the number of items on the list, I++, and then we need current thing, so that's, what do we got, workers here?
All workers at position I.
Okay, so notice the way I wrote that. You can always go back now and go, oh, really, all that I have to do here is just print out all workers sub I, because that's probably not buying you much. So we'll just take that thing and we'll now substitute it into there. And get rid of that. Okay, so that's calling the toString for the thing. And then it might be nice to actually bracket the individual items so you can see them. This is just going to run them all together, but we'll just leave it like that for now so that I don't crud up the code with some extra brackets. Okay, so something along that line, but there's that idea of writing it inside out rather than worrying about the loop first, okay, on something fairly simple. Okay, so there's the toString. Now, next problem. That thing right there. As soon as we go over 10 things adding, what's going to happen?
You're not going to be able to.
Also, it'll have an error.
It'll have an error, it'll die. This index out of bounds exception when you hit number 10, because that thing doesn't exist. Okay? What should happen there?
Should create a new array that's bigger and move everything over.
So this is like running a business, right? This is like me running my member list warehouse business, and somebody comes along and I've started my business with this small space of holding on to things for people, and I can only hold 10 things, and all of a sudden business gets really good and I have to expand. So I've got my warehouse that can only hold 10 things. I guess I need a bigger place to put stuff. Okay? So I'm going to go rent some other space someplace. I'm going to move all of my belongings over to the other place, and I'm going to abandon the old space and just have all my business in one place. Okay? So now that we've got the concept, let's do the same thing here. Where are we going to first discover that there's a problem with space?
If next free to fill is the same size.
So which, it's in the add thing to start with, right? Because somebody comes along and says, here, store this for me. How do you know you've run out of room?
This next street to fill will be the equivalent to the size of the array.
What's the size of the array?
Array or all workers size.
Close. You want to use size, but it's actually a variable in this case, length. What would you like to do? Give me one word that describes what you'd like to do.
New.
Copy.
Sure. I'm feeling lazy. Okay, so here's another concept, right? As soon as you start to go, well, it's this and this and this and this and this I'm going to have to do. One good thing to do is to just make a word for it and then worry about what to do later. Okay? The two approaches are either write a whole bunch of code to start with and then go, oh, okay, I got to clean it up. This is an idea, this is an idea. Let me separate out the ideas. The other approach is to go, oh, okay, it looks like I got to do a bunch of stuff here. What's the idea? Oh, the idea is I need to expand. I'll worry about the details later. Okay? So either way works. So this is the other approach of just being lazy and go, oh, okay, I'm going to have to expand. Now, the interesting thing about this approach is look what it does to the code. The code just becomes, oh, if I've run out of room, I guess I have to make a bigger space someplace. Presumably, after you've made the bigger space, you're still going to continue on doing whatever you needed to do. Okay? So this code works, even if it works if you expand, it works if you don't expand. You always know at this point that you've got enough space. Okay? So now you can go down here and you can say, okay, now we'll worry about private void expand and figure out how to do that. Okay? So what did we say was the first thing that you do if you needed to expand?
Make a new array.
Go rent some more space, right? Okay, well that's fine. So let's do a worker array just like this one. Only this is going to be new space. We'll make a new worker array. How much space do you want to make?
Next street to fill.
How about just adding one?
Then you'll be doing that every single time over and over.
But you don't know
Then you
how
have
often you'll
extra
be doing
room
it.
if you don't do that.
Yeah.
How about just adding a billion?
In other cases, there's no.
That might not be enough too, depending on how big it is.
Well, okay, so we're at this question of, if this is a business, and I see my business is going to grow, I know it's going to cost me something to move to a new space. I know that the number isn't 1, because I'm not going to go to all that trouble to move just to get one space. What's a good number? Can't make it too large, because then your business is renting a whole bunch of space that it doesn't really need.
1.5 times.
You could do, let me just add another 10 or 100 or something like that. The problem with adding a fixed number is that it's also labor intensive. Okay? So we're going to pull a little trick here, and let's add 2 times however much space we've got now, which is all workers.length.
So it always remains proportional.
Oops, I don't need private on there. Now, interestingly enough, the good thing about doubling in size, remember that little chess program, or that little chess scenario of, oh, okay, if we put a grain of sand on the first piece of a chessboard, and then we put 2 grains on the second, by the time you get to the 64th one, you've like got more grains of sand that are in the universe, or whatever it happens to be. That's the joy of doubling, right? Is that it's actually a fairly efficient operation to double the size. So in this case, we'll go from 10 to 20. And next time we'll go from 20 to 40, and then 40 to 80, right? So we basically get half again as much free space all the time.
But as it grows larger and larger, doesn't it become more inefficient?
Well, yeah, but you've got larger amounts of stuff, so if you have larger amounts of data, you're predicting that your business is also growing by that volume, so it's sort of a good thing, right? Because you don't want your business, you don't want to have to keep moving forever.
It would actually save you CPU cycles in the long run because you'd be less likely to have to do it again later in the future.
Okay. So it's always a trade-off. The trade-off is, you know, how much, it's officially called the space-time trade-off in computer science terms, right? Is you know, I can do stuff, I can make more space, more room, which makes things, you know, more efficient in terms of space, but it may, you know, if I decrease the space, it costs me more in CPU cycles to keep increasing it, right? So what do you want to trade? Do you want CPU cycles, or do you want wasted space?
CPU cycles are cheaper.
Right, either way. Well, we'll double it for now. Okay, so then what are you going to do?
You have to make all workers equal new space. Or
Well, we just made the warehouse space. What's the next thing we want to do?
Move everything over.
Got to move everything over. So we're going to go through all of the items we have. And I could actually use a for each here because the thing is full, but I'm going to stick with I equals 0, I is less than however many items we have. And now that, notice that's the entire array. And we want to move them from the all workers array directly across into exactly their same position in new space sub I. So what we did is we now said there's our new space, and it's now twice as large, and this is called new space, and we copied those things across there, and this was called all workers. And by the way, this is actually a variable that refers to that space. Okay, so I copied everything across one by one by one. Now what? They're in both places.
Are you gonna get rid of all workers?
No, and now you simply have new workers point to new space, and then make new space null.
See that number over there? If I take that number, new space, and move it over top of that thing there, then all workers stops referring to that chunk of memory and refers to that chunk of memory instead. Okay, so that's take the value that's in the new space variable and move it into the all workers variable, which is the simple slimy trick that says, oh, okay, you know, we're not over here anymore where we used to be. Our new address where you can find us is now this. Okay? So, this thing stops referring to this space. What happens to this space?
gets overloaded.
in Java.
We get tossed.
It just gets tossed. Mr. Garbage Collector will come along sometime later and go, oh, look, here's this huge chunk of memory that nobody's referring to. Let me just go reclaim that. What happens if I were a C programmer and did that? C programmers all over the world would be going, oh, did you just do that? How could you have possibly done that without doing the free beforehand? Because all of a sudden now you've got this big, huge chunk of wasted memory. Okay? So there's a big difference in, we don't have to worry about it in Java. We don't have to do any bookkeeping. It's just the space is gone.
Can you make new space null now as well, though?
Don't have to make new space null, because new space, the variable, is going to go away right away as soon as this method exits. And so then when that variable disappears, then it stops referring to the new space and life is good. So don't have to do anything with that variable. Okay? So there's the little trick. What happens if you get more than, we double this to 20 and we end up having more than 20 people in our union?
Double bit.
Just comes through again and doubles again, and now life is good. So we're running this like a good warehouse, right? It's like, you know, people just keep coming and bringing us stuff, and we never tell them how much room we have. We just go, okay, yeah, we'll take that. We'll go put it someplace. Don't worry, life is good, which is exactly what array list does for you. So this is almost everything that array list does as far as we've actually used it. It's just used it as a convenient way of managing stuff with an array underneath, because arrays are too dumb. Okay? Programmers used to write this stuff all the time without array list. They used to just go carve their own space, make their own arrays, keep track of where the endmost position was. A lot of C code still looks like it. The problem with that is that every, you know, if you forget one line of, oh, I added something and I should have bumped that number up, then all of a sudden you've got a bug which is very hard to find. Okay? So having these libraries means the goal is to use the libraries rather than ever doing the stuff yourself, because we've got unit tests that make sure that it works once and for all for everyone. Okay? The interesting question I want you to think about for next class, when we go to write unit tests for this thing, is the question of how do we unit test it? How do we know whether or not this thing is actually working for us?
Check the size of the array.
And in particular, how do we ever know that it's gotten bigger? I'll give you a hint. If we could get the capacity of this thing rather than the amount of allocated space, but the actual end position of this array, then we could keep adding things in and eventually discover, keep checking this thing, add, check, add, check, add, check. Eventually we'll go, well, hold it. Used to be 10 and now it's 20. I guess you've expanded. That's a good time to go unit test and see whether or not everything's where it should be. The question is it ever a good idea to give somebody that number? And we'll talk about that on Monday.